Hello dear students, I'm Dr. Moin. In this video we are going to discuss about solvent extraction, which is a type of an extraction technique. So let's start it. So first of all, introduction. In laboratory, whenever we synthesize an organic compound, so most of the time we get it in the form of insoluble form, and most of the time it is soluble in water. So generally we obtain our compound in pure form by evaporation, but sometimes our compound of interest is volatile or thermally unstable. So if we heat that solution, so we may lose our chemical compound. So for that purpose we need solvent extraction. So solvent extraction is among the various methods of separation. It is most versatile and popular method. It is the type of liquid extraction. So it's an extraction method in which the compound of interest is extracted from the solution to another liquid. So it's a type of liquid extraction. The separation can be carried out on a macro as well as micro level. So we can separate our compound which is present in the solution even in traces or even in large quantity, in large amount. It does not require any sophisticated apparatus or instrument. And another advantage is we don't need any sophisticated type of apparatus. So the apparatus is quite very much simple. The technique is used to separate the mixture of substances by selective transfer between two immiscible liquid phases. So as I mentioned earlier, that it's a liquid extraction. So the compound is made to transfer from one liquid to another liquid, and both of these liquids are immiscible into each other. Solvent extraction works on the principle that solute can distribute itself in a certain ratio between two immiscible solvents. So solute must distribute itself among two solvents which are immiscible into each other, and this distribution should be in a fixed ratio that could vary from solvent to solvent or solute to solute. And in what ratio they will be separated? So the components are separated on the basis of difference in their relative solubility into immiscible liquids. So in what ratio they will distribute themselves, that will depend upon their affinity with those two immiscible solvents. So definitely greater is their affinity with any solvent, so greater will be their distribution in that solvent, and vice versa. And then finally substances reach an equilibrium distribution between two phases, which are then physically separated, and finally there establishes an equilibrium of that solute among those two solvents, and then finally we separate both of these two solvent layers. So in this way we separate a part of solute from the solution. Now we will see the process of solvent extraction. So the process is performed using a separatory funnel. So this is the apparatus for solvent extraction, and this is called separatory funnel, and this can be fixed over on this stand. And here is the stopper over here, which can be open and closed. The sample whose components are to be separated are dissolved in a suitable solvent, which may be called solvent A. So as I mentioned earlier, that our sample may be already in the form of solution through which we are interested to separate the solute, or suppose we have we have solute in solid form, and that is actually the mixture, and we are interested to separate its components. So first of all, we will make its solution in some suitable solvent, and that solvent, first solvent, that will be regarded here as, represented here as solvent A. So now we have the solution of our sample. So this solution will be put into this separatory funnel. It will be closed below here. Then this solution will be put in this separatory funnel. Then this solution is shaken with another immiscible solvent, solvent B, in separating funnel. Then we will take another solvent which is different from solvent A, and this is called solvent B, and we will fill it in this separating funnel. And another thing which must be noted over here, that solvent B is immiscible in solvent A. So now we will close this separating funnel. We'll hold this separating funnel in our hand and we'll shake it so that there might be the transfer of solute from solvent A to solvent B. In this way, an equilibrium distribution of solute between two phases is achieved. So due to this shaking phenomena, ultimately there will be an equilibrium distribution of solutes among these two phases, among these two solvents, which is achieved. So in this slide, the process of solvent extraction has been shown in the form of figure. So we can see here we have the separating funnel, and we have taken it, the solution which is containing the solute, whose components we are going to separate, or we are interested to separate. So we'll add another solvent, solvent B, which is immiscible. So you can see here is the solvent B. And now after closing this separating funnel, we'll shake it, the separating funnel. So definitely the solute will start moving from solvent A to solvent B, which can be seen clearly here in the last diagram. In the last part, you can see the solute which have been shown here with the black dots. So they have transferred to the upper layer, to the solvent B. And how much they will be transferred, that will depend upon the their affinity with these two solvents. So the factors which determine how a solute will distribute itself among two phases are its polarity and polarity of each phase. So how much solute will be transferred from solvent A to solvent B, that will depend upon the nature of solvent and nature of solute. So if the nature of solute and solvent matches, so solute will move in that solvent, so which can be seen over here. If solute is polar and solvent B is also polar, so definitely more solute will be transferred into solvent B, and vice versa. And other factors which define the movement of solute to the solvent, that depends upon the degree of ionization, hydrogen bonding, and other electrostatic interactions. So these also play part in movement of solute particles from one solvent to other. Most of the time, solvent extraction procedures involve extraction of solutes from aqueous solution into a non-polar or slightly polar organic solvent. So as I mentioned earlier, that most of the time we are interested to separate the compound which is dissolved in water. So it is present in aqueous phase, which is a polar solvent, and our solute is volatile or thermally unstable, so we want to separate it. So our solvent B, so most of the time we choose the solvent B which is non-polar, or it is slightly polar organic solvent, and it could be the ether, hexane, chloroform, etc. So these can be used as solvent B. So here is an example. For example, an aqueous solution containing iodine and NaCl. So we have an aqueous solution in which there are present iodine and sodium chloride, and this solution is shaken with another solvent which is non-polar solvent, maybe ether. So iodine, we know that iodine is non-polar, so it will be extracted or it will be shifted into non-polar phase, that is solvent B, while NaCl, which is an ionic compound, so it will remain mostly in aqueous phase. So in this way both of these components will be separated. Solvent extraction, it can be used for various purposes, like in the preparation processes, in purifications, enrichment, in separation, and analysis on all scales. Now we will see the distribution law. Solvent extraction is governed by the distribution law, which is also called partition law. So the distribution of solute A, now we are going to represent solute by A. So the distribution of solute A between two immiscible solvent, in which one is aqueous and other is organic, is an equilibrium process. So ultimately there will be equilibrium, which has been shown over here, that the concentration of solute A in aqueous phase, that is in equilibrium with concentration of solute A in organic phase. Means when equilibrium has been established, so the quantity which is going to be shifted in organic layer, same quantity in the meantime is going to be shifted in aqueous layer. So ultimately their equilibrium has been established over here. So this distribution law, it may be stated as, when a solute distributes itself among two immiscible solvents and in equilibrium with each other, the ratio of the concentration of substances in two phases are constant at constant temperature. So solute distributes itself among two immiscible solvents. So when equilibrium has been achieved, so the ratio or the concentration of both of the substances of the components in two phases are constant. So that remain constant at constant temperature. So mean if we vary the temperature, so this ratio also varies. Another term used is the distribution coefficient. So what is this? It is the ratio of equilibrium concentrations in the two phases, which defines the distribution or partition coefficient, Kd. So at equilibrium, what is the concentration of solute among two phases? So it is the ratio between the concentration of solute in two phases at equilibrium. So it is represented by Kd and given by this expression. So Kd is the concentration of solute in the organic phase, and it is the concentration of solute in aqueous phase. So Kd, distribution coefficient, this is the ratio among these two concentration in two different phases, which can also be represented like this. So here square brackets represents the concentrations or activities of distributing solute species, which are represented by S over here. The value of distribution coefficient is independent of total solute concentration. Mean by varying the solute concentration, there is no effect on the value of distribution coefficient. Now we will see how efficiency of extraction is calculated. The fraction of solute extracted depends on volume ratio of two solvents. So how much solute is extracted, that actually depends upon the volume ratio of two phases. If a larger volume of organic solvent is used, more solute will be dissolved in this layer and vice versa. So it's clear from here that greater the volume of organic layer, greater will be extraction in this layer. The fraction of solute extracted is equal to the millimoles of solute in the organic layer divided by the total number of millimoles of solute. So simply it can be calculated that how much millimoles are present of solute are present in organic layer divided by the total number of millimoles of solute present in the whole in the two phases. And the percent extraction, it can be calculated by, so the concentration of solute in organic layer into the volume of organic layer divided by concentration of solute in organic layer into the volume of organic layer plus concentration of solute in aqueous layer into volume of aqueous phase multiplied by 100. So in this way the percentage of extraction percentage can be calculated, where V0 and Va are the volumes of organic and aqueous phases respectively. Choice of solvent. So in this slide we are going to see the characteristics of an ideal solvent B, means the organic solvent. So what should be the characteristics in that solvent? So a high distribution ratio for the solute and low for undesired impurities. So this organic solvent, it should have high distribution ratio for solute, means solute should be more soluble in this solvent, while the solubility of undesired components like impurities should be low in this solvent. Low solubility in aqueous phase, so either it should be completely insoluble in water, or it should be slightly soluble. It should be less toxic and with low inflammability, mean it shouldn't be catching fire. Sufficiently low viscosity, so viscosity should be very much low because we have to mix it with aqueous layer and we have to shake it. So if it is viscous one, so this process cannot be performed accurately. Then sufficient density difference from aqueous phase, so there should be the proper difference in density between these two solvents, aqueous and organic one, because they have to be separated from each other. Should be chemically inactive, so they should not react with each other. Should be cheaply available, so it should be cheaper one, because in this process we may also lose our solvent B, so it should be cheaper as well. And should be easy to recover, so it should be easy to recover, so we should be able to recover our solvent as well. In this slide we are going to discuss the densities of the two phases, that which solvent will form the lower layer and which solvent will form the upper layer. So the extractions lighter than water. So if we are using the solvents, the organic solvents like benzene, toluene, alcohols including butanol, pentanol, isopentanol, etc., then ethers including diethyl ether, isopropyl ether, dichloroethyl ether, etc. So if we are using any of solvent from these as organic solvent, so these solvents are lighter, means their density is lesser than water, so they will make the upper layer. So extraction will be, what do you say, in upper layer in case of these solvents. And while extractions heavier than water, if we are using the solvents like chloroform, carbon disulfide, carbon tetrachloride, etc., so these solvents, their density is greater than water, so they will form lower layer. So extraction will be in the lower layer in the case of these solvents. Now we will see various factors affecting extraction phenomena. So there are numerous factors which affect the percentage extraction. So some of them are being discussed over here. So first one is salting out agents. Extraction of metals can be enhanced by adding high concentration of salts to aqueous phase. This process is called salting out effect. So for example, we are going to extract some metals in organic phase. So this extraction can be enhanced by addition of some salt in aqueous phase. So there will be increased in concentration of ions in aqueous phase. So in this way, the metal of interest, the extraction of the metal of interest will be increased in organic phase, and this is called salting out effect. Another effect is the pH value. So the process of liquid extraction largely depends on pH. So it depends on the solutes. So different solute, their extraction efficiency varies with the change in pH value. So it also depends upon the pH. Another factor is the oxidation state. The selectivity of extraction sometimes may be increased by modifying the oxidation state of metals. So if we modify the oxidation state of metals, we can also change the extraction efficiency. For example, extraction of iron from chloride solutions, it can be prevented by reducing iron 3 into iron 2, which does not extract. Means if iron is converted into iron 2, so it cannot be extracted. So if we want to have greater efficiency, greater extraction, so we must have to keep iron in +3 state. Another factor is the masking agent. Sometimes metals are masked using some masking agents. So metal complexing agents, which are also known as sequestering agents, so these are used to prevent certain metals from forming extractable complexes, and in this way we can increase the selectivity of extraction methods. So there are various masking agents which are being used, and these include cyanides, tartarates, citrates, fluorides, and EDTA. So these are being used as masking agents. Another factor is the modifiers. These are the additives to the organic phase to increase the solubility of extractant in diluent. So sometimes these chemicals are added in organic phase which increase the solubility of the component in the organic layer. And for this purpose, high molecular weight alcohols, for example capryl alcohol, are commonly used as modifiers. So dear students, this is all about solvent extraction. Hope you did understand it. So if you like my video, then like it, and if you didn't subscribe my channel yet, then subscribe it right now. So thanks for watching. Thank you very much.